Hello, and thank you for joining us for this short presentation brought to you by the Oregon Housing and Community Services Multifamily Energy Program. In this module, we'll be covering an emerging technology known as heat recovery ventilation. Now, in all fairness, heat recovery ventilators and their sisters, energy recovery ventilators, have been in use for well over 40 years. That said, only recently have we seen strides in the industry to bring down the costs, available options and sizes, with increased efficiency and efficacy in heat recovery ventilators to make them a reasonable selection and choice for both new construction and multifamily energy retrofits. We should probably start by talking about what an HRV or ERV are. An HRV is called a heat recovery ventilator, or in general, heat recovery ventilation. Heat recovery ventilation is a balanced mechanical system with equal amounts of supply and exhaust that transfer heat between the two airstreams. This means the amount of air that is brought out of the building by the ventilation system equals the amount of air being brought in, and a percentage of that heat is transferred from one stream to the other. Energy recovery ventilation works in a similar way, but also transfers some of the moisture and therefore a little bit of the additional, what we refer to as latent heat, between the two airstreams. Both of these systems work without actually combining the air being exhausted with the air coming in. Rather, in both cases, they go through an energy or heat recovery core, which works as a heat exchanger to transfer heat between the airstreams. Let's start talking about heat recovery ventilation and the pros and cons of its use during different times of the year. An HRV in summer introduces outdoor air with all the potential moisture and higher temperatures that come along with it. The higher efficiency models will transfer incoming heat better to the exhaust air, ensuring that the unit is not operating as a heater during the summertime. In the Northwest, particularly in spring, an HRV can also add additional moisture to the building through the ventilation cycle because the heat is transferred from the incoming outside airstream to the return airstream leaving the building, which cools that supply air. But the exterior moisture is not removed from the incoming air. This building's dehumidification load then increases as a consequence of additional moisture from the outdoor air. Again, this is potentially really only a con in the spring in the Pacific Northwest. It is a much bigger concern in other parts of the country. An HRV in the winter allows heat to be transferred between the two airstreams at that recovery energy core I mentioned, but the moisture in the return air is not transferred to the supply air as it's exhausted from the building. And therefore, the moisture is actually able to be exhausted, and as a result, controlling the indoor relative humidity in the winter can be less challenging with the heat recovery ventilator. So overall, it's most definitely a pro for its use in the winter and for the majority of the summer, with only some real concern in the Northwest being for those spring or rare humid months. For most of the Northwest, an ERV or energy recovery ventilator is not necessary or even recommended. In rare cases where buildings are located in high moisture marine climates, for instance in a rain shadow, in a deep valley, or areas protected by mountainous terrain, an ERV in the summer can reduce the amount of moisture in the outside air that is delivered to the inside of the building. Heat and moisture are transferred to the exhaust airstream, reducing both the cooling and dehumidification loads of the building associated with ventilation. For eastern Oregon, or at very high elevations, and when the buildings are very tight, an ERV in winter transfers both the heat and humidity to the supply airstream at the recovery core. As a result, the building may not suffer from too much dry air with winter operation of an ERV. Overall, ERVs can be slightly more efficient than HRVs as they transfer both the sensible heat as well as some of the latent heat through the moisture. That said, medium and high-end manufacturers have spent considerable time and effort ensuring that HRVs are maximizing their efficiency. So as stated above, the benefits gained with an ERV are truly only realized for buildings in very humid climates or in very tight buildings that are located in very dry climates. At this point in time, we'll talk a little bit about some of the energy performance terms we associate with these devices. We'll start with sensible recovery efficiency, or SRE. The SRE is a percent of the recovered sensible heat compared to the total available heat. For instance, if an HRV has an SRE of 55% for a given flow rate and temperature difference, this means that the HRV core transfers about 55% of the available sensible heat in the outgoing air to the incoming stream. ASE, or apparent sensible effectiveness, is calculated by including the heat transfer from the high energy using fans to the airflow, as well as any heat that leaks in or out of the HRV case, and any leaks that may happen between the air streams as they cross through the HRV core. It's also expressed as a percentage and is equal to the temperature rise of the incoming air divided by the temperature difference between indoor and outdoor air. Effectively, the ASE will be a ratio of how well the temperature transfers between air streams. TRE, or total recovery efficiency, gives the net energy that is recovered by the ERV, which includes the sensible heat and the latent heat, or the temperature and the moisture that is recovered. It's similar to the SRE, except that it also includes that moisture recovered from the exhaust air. For energy calculations, we typically use the SRE or TRE. For comfort, we usually talk about the ASE. Let's take a little bit closer look at why that is. So why do we say that the apparent sensible effectiveness, or the ASE, is such a big deal? Well, let's take a look at two different ASE models, an entry-level model HRV and a high-efficiency model HRV. If you look at the word entry-level model on the graph in front of you, and you see the gray box above it, that is representative of, if you go straight down to the x-axis, about a 69% ASE model. That's fairly common for the entry-level models on the market. If you go over to the right and go down from the gray box above the high-efficiency model, you'll notice that there's an ASE of closer to 87 or 88%. It's important to note the difference between these two because we're going to look at the delivered air temperature at different outdoor temperatures. If we take a 20-degree outdoor temperature, that is the orange line, or the second line from the bottom that's going diagonally. If the outdoor temperature is 20 degrees, with the entry-level model, the air being brought into the building is going to be around 53 degrees. So when it's really cold out in winter, you'll bring in 53-degree air. That's still not bad, and it's much better than bringing in 20-degree air. But compare that to the high effectiveness model, the high ASE model. At that same 20 degrees, it's bringing in 64-degree air from the outside. So we have to ask ourselves which of these systems is most likely to deliver comfort to the building during that cold winter month. Research in Canada actually shows that models with lower ASEs are more likely to be shut off by homeowners and tenants in their buildings due to the pure comfort issue. And if we go through the trouble of spending the money to make sure we have a balanced ventilation system, we really want to ensure that it will not be disengaged by the tenants. This becomes a bigger deal as our codes get better and as we make our buildings more efficient, because it really becomes critical that we meet our ventilation requirements. We can look at some more definitions and some efficiency data online. The Heating and Ventilation Institute, also known as HVI, can be found at www.hvi.org. For those of you that work in HVAC regularly, you're probably familiar with AHRI, which is a product directory for heating systems and cooling systems. HVI works very similarly. It is a product directory for ventilation systems. And you can actually click on this green box that says HVI Certified Products Directory and actually look at and download specification sheets, and you can find the ASE, the SRE, and the TRE for each different model that's available. We know that some manufacturers make very nice claims about their products, but if they're not listed on HVI, then we have no real way of knowing exactly what it is that they're reporting on. So it's our highest recommendation that any product you purchase, actually has a product rating available on HVI. Beyond basic efficiencies and whether or not you're using an HRV or an ERV, there are also some other considerations that need to be taken into account that may really be different between a new construction building and an existing building. For instance, in new construction buildings, depending on if you're building a low-rise or mid to high-rise building, you're going to be required to meet ASHRAE 62.2 or ASHRAE 90.1. These are ventilation standards brought to you by the American Society of Heating, Refrigeration, and Air Conditioning Engineers. These are designed, again, to make sure that these tighter buildings are properly ventilated. 62.2, on the other hand, is really focused for low-rise multifamily and single-family homes. These ASHRAE standards are constantly evolving, and they actually prefer balanced ventilation. In fact, future iterations of code and future iterations of the ASHRAE standards are considering adding penalties to buildings that do not build with balanced ventilation. So if you want to use the least amount of outdoor air to be pushed into a building, starting with balanced ventilation will be important. With existing buildings, there's not the same level of requirement, but it still should be considered, particularly because taking activities such as replacing siding, insulating buildings, changing out windows and doors are all likely to make an existing building tighter. And when we do that, the need for ventilation is going to really apply. Beyond that, there's what we sometimes refer to as the constructability. And it's going to come down to how we design these. We use the term HVAC a lot, which stands for heating, ventilation, and air conditioning, or as some installers refer to it, heating, venting, and cooling. When we put in something like a balanced ventilation system in new construction, we can actually rearrange those and think VHAC. We can put ventilation before heating and cooling because it will actually impact the loads that need to be met by the heating and cooling equipment. When we look at existing buildings, we may be limited by the building's dimensions and some of the existing equipment that's already there. So we tend to think of them as two separate approaches, heating and cooling and V for ventilation. Again, the need here is pretty critical in new construction. We're building much tighter buildings that really do need to make sure that we get air moving to all the places it needs to move. A different way to think about that is new buildings need a system to help them breathe. Now, existing buildings are typically leakier to start with. And what we really want to think about there is when the building is breathing. If we leave it up to Mother Nature and the forces such as stack effect, warm air rising, and wind effect on buildings, wind blowing and moving air in and out, we're no longer in control of when the building is ventilating. So paying attention to smart, balanced ventilation strategies help us determine when the building breathes when we update existing buildings, and they help ensure that they breathe at all when we build these tighter new construction buildings. In new construction, we also have some opportunities to reduce some of the costs of installing a heat recovery ventilator by using some of the exhaust ports in half bathrooms, kitchens potentially, and laundry rooms or utility rooms. We still recommend potentially using a kitchen range hood and an exhaust fan in full bathrooms, as an HRV may be running at a very low speed for long periods of time. And we find that sometimes tenants and condo owners like to see the fog go away from their mirrors in less than 20 minutes. And you simply may not get that with just using an HRV. The control strategy is going to be a little different for existing buildings. But again, because we're likely tightening these buildings by performing some of these other weatherization measures, we may still have some of those considerations. What we're really going to be faced with, however, in existing buildings are things like, what is the ductwork like for the existing heating and cooling system? How about the chaseways and the building cavities? Do we actually have room to run a heat recovery ventilator, or do we need to tie it in to the central heating and cooling system to make it all work? So different considerations, different needs, different designs between existing and new construction buildings. When it comes to control strategies, the strategies themselves are actually pretty similar, whether we're talking about the coastal marine climate zones or the non-coastal climate zones, such as Eastern Oregon. Those are often referred to as climate zone 4C in Oregon for the marine climates, i.e. west of the mountains, and zone 5 in eastern Oregon or east of the mountains. The real difference is what building tightness level do you use a different control strategy. For all tight buildings, which we think of as below 3 air changes per hour at 50 pascals, which is a tightness mechanism, we think of continuous low speed with manually operated high speed. Effectively, you set the HRV to continuously move a small amount of air, and there's literally a boost button that a tenant or condo owner can hit to turn the system to a higher speed for the times you really need to move more air. As the building gets a little leakier, you move closer and closer to strictly on-off and time of day timers. The real critical difference here is, again, when you want to make that move. It's different for the marine climate than it would be for the eastern climates. And that's because if we think about it, in eastern Oregon, the winters are much colder for the most part and much hotter in the summer, so we want to have a little bit tighter level of control. There are actually potential influences on the Oregon Multifamily Energy Program incentives as well, particularly for builders and developers who are choosing the whole building path. The way the whole building path is done is each tier is based on a percentage of electric savings over existing conditions. So in a retrofit, that's literally over the way the building was modeled and its existing condition. And for new construction, it's going to be based on the current code. The higher the modeled savings are that are achieved, the higher the project's incentives. So you look here, you can actually see for Tier 3, we actually pay out a higher incentive rate per unit of energy saved than we do for Tier 1. That extra bonus that you get by bumping up to a higher tier can often be achieved when you're combining heat recovery ventilation with building tightening as a measure. So you may actually be able to build up and get to a higher incentive level by tightening up the building and using heat recovery ventilation. With that, we'd like to thank you for watching today's short presentation. There's more to come, so we hope that you've enjoyed this, and we hope that you'll check out our other small short presentations.